Welcome to my seminar talk on logical relations for logical framework, sketching the equine paper by Florian Rabe and Christina Sojakova, which appeared back then in 2013. So I've been working with logical relations the last couple of months, starting last year in my master's project, and then continuing in my master's thesis, and now presenting them as part of my master's seminar. And I would say that it took me these 3 courses to get a solid, basic understanding of them. So logical relations are not an easy topic, and they certainly are not a topic which you can just learn about in one talk and just be great with them. So in this talk, I hope to convey some basic ideas, some basic motivation of what logical relations are and how we can encode logical relations in a logical framework. So as the first thing, let us detangle the words on the title of this talk. And this gives rise to 3 separate terms, and these 3 separate terms also make up the outlet of this talk. So this talk will be structured into 3 parts. The first part will be about logical relations and then about logical framework, and in the final part I will combine both. At this point, I would like to give very rough explanations of those terms and later go into much more detail. So logical relations, they are a class of proof methods. So in many type theories, you would like to prove some meta theorems such as strong normalization. So for example, in the simply typed lambda calculus, you would like to prove that if you got a well-typed term and you better reduce, then this terminates sometime. And this is known as strong normalization. And usually such meta theorems in type theories, you can prove via proofs by logical relations. So this makes logical relations particularly important in the study of computation, programs, functional programming. Now, logical frameworks are something fundamentally different or orthogonal. In particular, the adjective logical, as in logical relations and logical framework, they do not bear any similarity. So the logical framework has the idea that we got many logics and type theories, and they all got some kind of syntax, maybe some form of binding, substitution, and so on. And it would be really cool to have a uniform language to formalize all those logics in. In particular, no one has motivation to re-implement binding and substitution for every logic there is out there. So this is something a logical framework hopefully outsources for you and provides you with support for. Now, if I say that logic relations are found in the formalization of many type theories and logical frameworks allow you to formalize many type theories, so why not have maybe a uniform notion of a logical relation in just the setting of a logical framework? So the whole idea of this paper by Florian and Christina is very roughly, here are many type theories and you can prove things in every type theory via proof by logical relation. Here's a logical framework in which you can formalize many things. So why not generalize all those specific instances of proofs by logical relations to a very general instance, notion of a proof by logical relation, just on the setting of a logical framework. So this is the whole idea. And now let me give you some more motivation. I already sketched some motivation, but let's be a bit more concrete. So to formalize a type theory, we have to formalize the following things. So we usually got some syntax, some typing rules, and some operational semantics such as better reduction in the case of simply typed lambda calculus. And implementing or formalizing all these 3 is already tedious and daunting enough. And now comes the part about proving meta-theorems. And we all know that proving things in a proof assistant is already hard enough. And here comes the whole problem which motivates the paper, right? So meta-theorems and type theories are often proven by a proof by logical relation. And the formalization of such proof by logical relation usually would involve, without this work, also formalizing the specific theory of logic relations just in the setting of this specific type theory. Okay, so you're at the point where you would like to prove some meta-theorem in this type theory, and then only to end up formalizing the whole theory of logic relations for this type theory. Okay, so far so good. And then you prove your meta-theorem, and what you get is sadly only limited representation and only limited tool support, because your formalization of logical relations was specific to this type theory. Now, with this work and some 1/epsilon amount of work, we could have a uniform notion of logic relations and then just formalize our type theory in the setting of a logical framework, and then just instantiate that uniform notion, and thereby, or by the idea of a uniform notion, we get very general representation and general tool support. So these are also ideas that Quarkies, the members of this research groups, also resonate with, I hope. So yeah. Before I really dive deep into the much more detailed explanations, let me just simply state the required background knowledge. So I assume you know the simply typed lambda calculus. We are going to recap it and going to prove strong normalization later in it, just for you to get a feel about how logic relations are used there. But really, if you have never heard about simply typed lambda calculus before, you're maybe going to have a hard time. Also, I assume you know how to formalize things in a logical framework, for example, in the MMT system. So far, so good. So let us start with going deep into logical relations. So as I said, they are a class of proof methods used to prove various things, various meta-theorems in type theories. Note that they are not a formal class, so they are, you might call them an informal class of proof methods, because usually authors in different articles use different flavors of logical relations and proofs of logical relations. Yeah, and the things you can prove with it is well, strong normalization that I already talked about. So this has some pretty realistic motivation too. So strong normalization says if you have some kind of functional programming language and you have coded some program and the compiler says this type checks, then you're guaranteed that at runtime your program will terminate. And complementarily, type safety says if the compiler says your program type checks, then your program won't throw any exception at runtime. And strong normalization, type safety together say if your program type checks, then it will terminate successfully at runtime. So these are very useful properties to actually have in practice. And both are proven by logical relations commonly. Also, you can prove program equivalences using logical relations, such as correctness of compiler optimizations, or the very well-known theorems for free you can also get via logical relations. So this theorems for free was a well-known paper by Philip Wadler, and there it is proven that say in some kind of type lambda calculus with quantifiers, for example, some f, you can prove that terms of this type for all alpha, alpha to alpha, well, those are precisely the identity. So all terms of this type are up to some alpha, beta, eta equivalence. They are lambda x dot x. So just by looking at the type, you can extract some very useful information. And this is one of the key points from logical relations. Right, so in the following, for you to get a better feel for what logical relations really are, let us dive into a proof of strong normalization of the simply type lambda calculus. So let us just recap some syntax to get on a common ground. So the terms are as usual. So you got variables, lambda abstraction, application. As types, you got some base types B and simple function types. And contexts are effectively lists of typed variables. Then the operational semantics, for which we would like to prove strong normalization later on, says if t reduces to t prime, then lambda xt reduces to lambda xt prime. So you can reduce under a lambda abstraction, and this is beta reduction. You can also reduce under function application, namely in the function position, and you can also reduce under function application in the argument position. And now if we define Sn to be the set of all strongly normalizing terms, then we can state strong normalization as follows. If T is well typed in some context gamma, then T is strongly normalizing. Note that I will omit the typing rules for brevity in this talk. So naively, you could try proving this statement just by induction, because evidently this statement is universally quantified over context gamma, terms T, types T. So you might as well try induction on terms T. So, excuse me, in the case of variables, this is trivial because variables are strongly normalizing almost by definition. You cannot apply any reduction rule anymore. For lambda abstraction, what we do is we exploit the hypothesis, namely that the input term is well typed. So we can invert the typing judgment. So this was our hypothesis. And by inversion, we get that in some other contexts, S, the actual body of our lambda abstraction, is well typed too. And then we can apply the induction hypothesis on this thing here to get that S, the body, is strongly normalizing. And if we can't reduce under the lambda abstraction well, then the whole lambda abstraction is strongly normalizing too. So in this case, we are done. Let us continue with the case of function application. Okay, so let us again invert the typing judgment. We get that S is well typed with some function type, and T is well typed with some compatible with the argument type S. Now by induction hypothesis, actually applied 2 times, we get that S and T are strongly normalizing. But here's the culprit. We don't know anything about S or T applied to S. So we know that S, T are strongly normalizing, but we can't combine them. Namely, what happens if S is, sorry, this should be an equal sign. What happens if S is lambda x and somebody? Then certainly we could, with ST, we could do one step of beta reduction. Sure, and then we don't have any hypothesis in our context currently to proceed reasoning. to proceed reasoning about strong normalization of S. So what happens? What do we usually do if an induction fails? Well, we strengthen the induction statement. And concretely here, we would like to strengthen the induction hypothesis on S. We would like to say that S is strongly normalizing, and ST should be strongly normalizing for arbitrary terms T, where T is also strongly normalizing. So we would like to encode actually the point where we were stuck into the induction hypothesis. Notably, we would only like to do this on those S of function type. So we would like to strengthen the induction hypothesis only on some terms based on the type. This is the whole idea of logical relations. So let us try our first formulation and prove with a logical relation now. So with a logical relation, the reformulated statement looks as follows. So we say that if T is well-typed in some context, then T is in some relation specific to the type T. And how does this relation look like? Well, at base types, we are just as before, we just say that, well, values of base types should be strongly normalizing. So this is no gain over the previous statement. But then on function types, we say S should be strongly normalizing. And for all T, possible arguments T of the right type, if they are in the relation, then ST is in the relation too. So for every type T, we specify a relation on terms of type T. We give a type index family of relations. And if we could actually prove this formulation, then strong normalization would be a corollary, namely, we would just, so given a well-typed term T, we would apply this theorem, and then we would get that T is in the relation and by its type, and then we would just project out this these parts here, right? So strong normalization would be an easy corollary. Now let us try to prove this. Well, the case for variables now is no longer trivial. It's a bit subtle, but it's doable. But let us ignore this issue for the purpose of this talk. Let us rather focus on the other cases. So for function application, we can invert the typing judgment and now get that S and T are rel-typed, and then by the induction hypothesis on S, we can instantiate this here, right, with T, and then we get that S, T's in the relation. Yeah, and precisely this is not surprising because we just encoded this step into our logical relation. Now the case for lambda abstraction now isn't as easy as before, and this is to be expected, right? If you strengthen the induction statement somehow, some cases will get easier, some cases will get more complicated. And this is the case here. So we invert the typing judgment again and now get that S is well typed, the body of the lambda abstraction. Now we have to prove the above thing here. Now lambda XS is strongly normalizing because S was in the relation, and if something is in the relation, we can project out the strong normalization property. Now, what do we do with the right conjunct? So let us just introduce T and this hypothesis. Then we need to prove this here. Well, what is this? We just let us just naively try to rewrite this. Lambda x as t should be in the relation. Well, if we just assume that being in the relation is stable under beta reduction, then this amounts to saying that s applied with the substitution is in the relation. But now we are deviating from the induction hypothesis as by a substitution. So again, we are stuck. But resolving this issue this time by closing the logic relations under substitution actually is successful. So this final formulation, where the logic relation is closed under substitution, goes through. I won't show the proof in this talk, but you can find the proof of this in the references at the end of these slides. Notably, here we say if t is well-typed, and here's some condition you can ignore, then t applied with the substitution gamma is in the relation. And now we can get strong normalization by instantiating gamma with the identity substitution and then projecting out these parts again. So again, strong normalization is an easy corollary. And this brings me to the summary of logical relations. So our motivation was strong normalization, a meta-theorem in some type theory. Mere induction on terms failed. The induction hypothesis was too weak in some cases, and we needed to strengthen the induction based on the type of terms. And this brings me to a very general pattern of proofs by logical relations, a pattern you can find in the literature. So in every proof by logical relation, what you do is you first define a logical relation. So for every type T, so know that you're working in a type theory, and a type theory gives you types. And for every type, you specify a relation on terms of that type. And then after doing this, you go on and prove the so-called basic lemma or fundamental lemma or parametricity that says if a term is well-typed, then it's in the relation given by its type. And finally, in the general pattern, you can usually recover the desired theorem as a more or less easy corollary. In the rest of this talk, or the idea of the rest of this talk, is to bring this general pattern into the world of logical frameworks. And for that, I will first introduce logical frameworks. So for the motivation, the starting point is follows. There are many logics out there. So first order logic, sorted first order logic, higher order logic, extensional type theories, intensional type theories, and all those logics and type theories that I forgot mentioning here. And all those logics have something in common. They all got some abstract syntax, usually some binding and substitution in some form or another, and usually some proof calculi with rules, where rules can also be schematic and rules can also have side conditions. And now imagine you wanted to implement a proof development environment. Imagine you wanted to implement some kind of editor or IDE for the PC for you to enter this abstract syntax, this binding and substitution, and for you to enter proofs over these proof calculi that the machine checks afterwards. And surely this is a daunting task. This is even a daunting task for one logic, and doing the same for different logics is unbelievable complicated, or rather time and error prone. So what you really want is a uniform presentation language, which gives you some very general features for abstract syntax, some uniform way to say, oh, this is a binding construct, this is a substitution construct, and that's it. And this is what a logical framework gives you. So let me elaborate a bit on 2 points here. The first point being binding and substitution. So even implementing or formalizing the simply typed lambda calculus which has arguably the most simple form of binding is a daunting task to do in Coq. So naively you would say, well, it's easy on pen and paper. Where's the hassle doing it in Coq? Well, on pen and paper, you formalize binding via strings, roughly, right? If you say lambda x dot body, this x is a string, and within the body, you can have references to that string. So you got string references within the body. But now you face the issue in, say, even with pen and paper, you face the issue when defining beta reduction that you only can do so modulo alpha renaming, because you might have name clashes every now and then. And accounting for name clashes and introducing fresh variable names is a hassle when formalizing things. Sure enough, this is possible to do in Coq, even with strings and string references, but imagine you're in the middle of a big proof and then out of nowhere you need to introduce some fresh name and deal with fresh names all over the place. And this is daunting. So even implementing binding substitution for the case of simply typed lambda calculus is non-trivial to do in Coq. And now to my second point. Implementing proof calculi isn't that easy either. Because say you already formalize something, say an inductive type for the abstract syntax, for proof calculi, you need to formalize yet another inductive type. And if you imagine that you're developing an IDE, then this means that you would need to implement autocomplete, syntax highlighting, quick fixes, refactoring, and so on. Again, maybe you have already done so for abstract syntax, but now you have to do it again for the proof calculus. And imagine you already formalized or implemented some kind of type checker for the abstract syntax. Well, now you have to formalize yet another proof checker for the proof syntax. And logical frameworks very much help here by unifying the syntax for proof calculi in the abstract syntax. Logical frameworks use something that is known as judgments as types and propositions as types. And we can, in a logical framework, we encode proofs just as normal terms of the abstract syntax. And this means that proof checking amounts to type checking of the abstract syntax. And hopefully the logical framework already implements decidable type checking for you for the abstract syntax. And this means that proof checking is something you get for free. So these are all selling points of a logical framework. But there's one more selling point, notably in the realm of this talk, namely, there are many logics and there are also many type theories. And many type theories have a notion of a logical relation. So isn't this something similar to the same thing I said about abstract syntax, binding, and substitution? And it is. So you could say that implementing a general notion of a logical relation just in the setting of a logical framework is just a natural extension of the fundamental ideas of a logical framework. So in the following, I will introduce one logical framework, the so-called Edinburgh logical framework. And usually when I say LF or write LF on slides, I mean precisely this framework. So let me introduce to you LF right away in conjunction with MMT. So MMT gives you a module system over LF. We formalize knowledge, say set or type theories and logics, into theories of declarations. So a theory is as some kind of entity and effectively a list of declarations. Now, a declaration can be two things. Either it is an include or a constant declaration. Include declarations serve to allow you to have modular theory graphs of formalizations. So includes are just there to give you modularity for all the reasons that software engineers like includes, imports, and packages. And constant declarations are the actual bread and butter of your formalization. They are the actual thing that makes up your formalization. A constant declaration has an identifier C, a type component, and some optional definitional component. And both the type and definitional component are terms over some dependent type theory, and this is LF. So this comes from MMT, and now this comes from LF. And there we go. Well, a term can, ignoring this type, a term can either be a reference to a constant identifier, a variable, function application, lambda abstraction, and a dependent or simple function types. Let me give you some example. And this is going to be the running example throughout the rest of this talk. Suppose that we wanted to formalize propositional logic. And with usual pen and paper, we would do as on the left here. We would maybe give a BNF grammar, which says that there are atoms that we leave unspecified for the moment, and there are propositions, and a proposition can either be atomic, that is a reference to an atom, be the negation of a proposition or conjunction or implication. So in MMTLF, we would formalize this as follows. We would write theory PL. Then we would spare ourselves one type for propositions. So we would write prop colon type, and this allows us to use prop as a type afterwards. So negation, conjunction just become functions of function types of a prop. And to give you one example of a defined constant, let me show you how we could formalize implication here. So implication again has an identifier, a binary function type. And here the definition says, well, lambda p, lambda q, we just take those arguments and then we do discrimination, negation, and conjunction, which hopefully is morally equivalent in some sense to the usual implication. But in the rest of this talk, I will ignore implication just to keep examples short. That's why it's grayed out here. You might ask yourself where the atoms have gone. Well, we have them implicitly in our formalization. Namely, if we have, suppose we had an atom here, A, then here we would write A colon prop. So in our formalization, we encode atoms by constant declarations of type prop. Now, I said that the goal of this talk is to eventually combine logical relations in a logical framework. It turns out that formalizing conventional proofs by logical relations such as the one for strong normalization we've seen, is still pretty complicated, and even more so to do within a talk. So what I want to get at is I would like to show you later some proofs by logical relations, not over the simply typed lambda calculus, but over this theory PL of propositional logic. And for this reason, I've already introduced you to the syntax. Now, since we will be using logical relations to prove something, it makes sense to also introduce a proof calculus. Also, you can see the judgments as types paradigm here. So let us implement this PLND for propositional logic natural deduction. And in this theory, we include PL, okay. And now we spare ourselves one derivable symbol, which for every proposition gives us a type. And we think of it as follows. So given a proposition P, we say that P is provable, or we think of P as provable, morally at least, if and only if this derivable P is inhabited. So for every proposition P, derivable P is the type of all proofs of P. And natural deduction rules are now just constructors of such derivable P types. So for example, double negation introduction is a dependent function. It takes a proposition P, an inhabitant of derivable P, that is a proof of P, and returns an inhabitant of derivable not P, that is a proof of not P. Now, since this double negation constant here does not have a definition, this is to be seen as some kind of axiom. So axiomatically, we return an inhabitant of this derivable not P type. Analogously, for conjunction introduction, we take two propositions P and Q, a proof of P, a proof of Q, and axiomatically return a proof of P and Q. And same for the other rules, which we can do analogously. So here you can already see that schematic rules, which many logics do have, we can very easily implement in a logical framework by having just dependent functions. Now, let me come to the final part of this talk. So we will combine logical relations in a logical framework. For that, recall this pattern of a proof by logical relation, this pattern that is found in the literature. And our goal now is to encode this pattern in a logical framework. So, and for the purpose of this talk, we will do this encoding only for the theory of propositional logic. Note that we can do this encoding in a very general setting. We can, and this is also what this paper by Florian and Christina does, but it's a bit cumbersome to define things that way, and even more cumbersome and notation heavy for a talk. So hence, let us just restrict ourselves to the case of propositional logic. So what was the first step? So the first step was to define a logical relation. So for every type, we have to give a relation. So given this theory PL, suppose we wanted to do a logical relation over PL. Well, so the first thing to note here is how can we encode this idea of something is a logical relation over something? Here we do it with some kind of trick, you might say, namely with the help of a theory PLR you might call the interface theory. So eventually, logical relations over PL need to be realizations of this interface theory. And now in this interface theory, we can add requirements on logical relations. So the first requirement was that for every type T, we have to give a relation. So for that, let us go through this PL and look at what types it has. Well, it only has one prop colon type. And for prop colon type, let us add one requirement in this interface theory at the bottom here. Namely, here we add prop R, and every realization of PLR needs to give a definition to all undefined constants. So a logical relation over PL in particular needs to give a definition for this prop R. And this prop R basically is the LF style encoding of a relation over propositions. So for every proposition P, it gives a type. So that's very similar to this judgments as types paradigm we've seen on the recent slides, right? There we had derivable prop to type. So derivable P was the type of all proofs. Well, here, prop R P is the type of all proofs of P being in a relation. So far, so good. Now, the second step in the, say, pen and paper setting usually is to prove the basic lemma. Now, in the setting of a logical framework, we can again employ some trick and combine some parts of the second part into the first part. Namely, if you maybe recall how we proved the basic lemma in the case of strong normalization, we had some kind of induction over terms, right? And induction means for every way we can construct terms, we have to have case. And this is actually something we can readily encode in our interface theory here. So in PL, we can read off of what kinds of ways there are to construct terms. So one way is to apply this negation constant. So this is one way of constructing terms, and hence we add one requirement here, which is to be read as follows. So realizations of this interface theory need to give a definition for this, and for it, they can take a proposition P, or they must take a proposition P, must take a P star, a proof of P being in a relation, which you can read as the induction hypothesis on P. And then definition need to give an inhabitant of not P being in a relation. So in other words, what definitions or what realizers of this theory need to do is for every proposition P and access to an induction hypothesis on P, they need to give a proof of not P being in the relation. And this is precisely what we did back then at the beginning of this talk in this induction proof we had for strong normalization. Just encoded into the setting of a logical framework. And finally, we also got some other form of constructing terms, namely conjunction. And for conjunction, we do similarly. So this might be a really large type component, but actually it's pretty easy. It just says for all propositions P, induction hypothesis on P. For all propositions Q, induction hypothesis on Q. You need to give a proof of P and Q being in the proposition. You need to give a proof of P and Q being in a relation. And that's it. So, because this is such a central slide, let me reformulate the whole slide again. On the pen and paper setting, we first had to define a logical relation and then proved the basic lemma. In the MMTLF setting, you need to give a realization of this interface theory. Thereby, you already give a relation for every type. And thereby, you already give the cases for the induction of what were previously the cases of the basic lemma above here. And given this, the second step actually here becomes, so here you needed to prove something, right? So we shifted the proof obligations of the second step here into this interface theory on one hand, and as a result, we get a basic lemma here as a second case for free. So here we can prove in a very general setting. So this is not something you have to prove. This is something Florian and Christina proved on the paper. If P is a proposition, so this is the LF typing judgment. If P types against prop, then in the realization hour on this interface theory, there's some kind of term RP, which I won't define, but this is something you can define, so there is an inhabitant of prop RP, and an inhabitant of a judgment as type means this judgment holds. So this means P is in the relation. And the third step above was to recover the desired theorem as a corollary. And doing so in MMTLF actually is not is an open question yet. We are not sure how to do it best yet, how to best expose the basic lemma within the MMTLF formalization system. Nonetheless, one very important point here is that realizations of this interface theory can already be given within the MMTLF system. If you know a bit the MMT system, realizations of PLR are just views with domain PLR. And this means that the MMTLF system already has support for checking whether something is a valid logical relation. So this is to be contrasted with the point here above, where proving the basic lemma would maybe entail, I don't know, doing elaborate proof checking, or at least it's not clear that the proof checking of the basic lemma here would be subsumed by type checking. But the way we did this here, checking whether something is a logical relation, is subsumed by type checking, in fact. Now, before giving examples, I'd like to give a bit more focus on the basic lemma. So the basic lemma here again said that if P is type checks against prop in our PL, then it's not in the relation, but there's some kind of witness for it being in the relation. So assuming P and Q are just two propositions, then really for every, no matter how complex term we might construct in PL, the basic lemma holds. So this gives rise to another viewpoint of what logical relations in MMTLF are. Namely, they prove statements all quantified over terms of a given MMTLF theory. This is an interesting viewpoint that I will catch up again in the future work section of this talk. So let us finally talk through some concrete examples of logical relations. As I said, there's no way I could present any realistic proof by logical relation, such as strong normalization, as part of this talk. This would be far too complicated and notation heavy. Instead, we stay in PL and prove two theorems, namely two theorems regarding non-constructivism. So the first one says if we are non-constructive by means of law of excluded middle. So if we are non-constructive in the atoms, then we are non-constructive on the propositions. And this is the flair of both theorems. And in the first theorem, we take non-constructivism to be law of excluded middle halts. And in the second, we take non-constructivism to be double negation elimination halts. Actually, that this is about non-constructivism isn't in any way related to logical relations. It just turned out to be some kind of very accessible and easy example to have here. So here you already see that the basic consequence here in the statement is something universally quantified over all propositions, that is over all terms of our PL theory, and the same holds here. So you might already guess how they are both instances of a basic lemma. So let's just do it. So on the left here, you see the theorem that we want to prove, and note that this here is a theorem on a meta-mathematical or meta-formalization level. And what we do is we would like to encode this theorem in our setting of MMTLF and this PL theory. And we do so by a MMTLF logical relation. So we give a realization of this PLR. This is our goal here. So let us write this theory TND. So we first include PL and then PL and D to have some kind of natural deduction rules, which will the purpose of which will become evident in a minute. And then we say from this point on, we realize this PLR. So we give a definition for every undefined constant in this PLR interface theory. And the first undefined constant was this R, and basically it was there to require us to give a relation on the propositions. And now to make an educated guess of what we can write there, consider the basic lemma for TND that we would eventually get if this TND would type check. We would get that if P is a proposition, then there's a witness TND of P, again, something I won't define. There's a witness of prop RP. So how do we need to choose prop RP? Well, if we choose lambda P, derivable P or not P, then the basic lemma becomes this. So if P is a proposition, then there's a witness of derivable P or not P. And this basic lemma is something you might call a faithful encoding of this meta-formalization theorem, right? I hope you agree. And next, we would need to give definitions for the cases of the induction, basically. The first one being negation. So we would need to prove that if P or not P, if we have that, then not P or not P that we have to show. And in fact, it isn't too interesting how this could be done here. It's a bit, it's not complicated, but it's a bit notation heavy and actually not interesting for the purpose of this talk. So just note that there's an MNPLF term we can write down here, and that it type checks. I think this is a point where you just need to trust me, because the goal of this talk is to convey how we can model logical relations in a logical framework and not how to construct hairy natural deduction proof terms. And in fact, the proof term for conjunction was too hairy for me to actually try, but it does work out, at least with the Fitch diagram I wrote or I tried on paper. So let us step back a bit and ask ourselves, well, is this basic lemma really a faithful representation of this thing here? So we have successfully represented the conclusion, but what about the hypothesis that we are not constructive on the atoms? There's no point in this formalization where this goes in. And isn't this surprising? Well, recall that we've treated atoms implicitly in our formalization. So if we had an atom in our theory PL, we would have A colon prop in PL. And hence, we would also have, in our interface theory PLR, we would have AR colon prop RA. So if we had an atom A in PL, we would also need to give a definition here to AR, namely encoding that A is in the relation. So in fact, the way how we encode things is faithful. It just treats atoms implicitly. Now on to our second example of double negation elimination. Now we got a very similar setup. We just renamed this theory to D and E now. And now for prop R, what definition do we give? Well, maybe it's evident now. We give lambda p, derivable p is equivalent to not p. Just encoding this here. And again, for the basic lemma, we precisely get this. So it makes sense to give this definition. And the case for negation, again, is some kind of hairy proof term, and for conjunction, even more hairy. So this concludes the two examples I had in mind for this talk. Now, let me come to the conclusion. So we've started off with logical relations, and they are an informal class of proof methods. They're used to prove meta theorems in type theories, which have a real-world significance, a strong normalization, and type safety. And they are usually called for when induction over terms fails, and you need some kind of strengthened induction hypothesis, and the strengthening, and if the strengthening somehow depends on the type of the terms. And in such cases, you can use a proof by logical relation, which goes on in 3 steps. We first define the logical relation, give a type indexed family of relations, and then we prove the basic lemma. And as a third step, we recover the desired theory. Now in MMTF, we represent type theories as MMTLF theories. And for every MMTLF theory, we can construct an interface theory for logical relations. We've done so for the theory PLR, resulting in the interface theory PLR. And these interface theories, for every type in the original theory, declare a relation. And for every case in the basic lemma, declare a constant which amounts to proving a case in the induction, basically. And then logical relations over PL or original theories are realizations of those interface theories. And if we got a realization of this interface theory, then we immediately, without proof, know that if P or if something types against a type in the original theory, then it is contained in the relation given by the realization for this specific type. So far, so good. And in this talk, we've only discussed how to do this encoding of logical relations by means of PL. But in general, you can do this for pretty much every MMTLF theory. Details you can find in the paper by Florian and Christina. But be warned, it's a bit notation heavy. So you really need to sit down and have a look at the notation. So given this, let me give you some more appetizer for future work. Or rather for future consideration, I should say, because the first point is something Florian and Christina already did in the paper. So we've just considered logical relations over an MMTLF theory. And we can now also consider logical relations that maybe or they relate modular view application. So far we said, well, over an theory T, logic relations over T, proof statements about terms T, all quantified over all T terms T. Now, the generalization now is, formed by Florian and Christina, given a view, which I won't discuss what it is here, but if you know what a view is, then carry on listening. Given a view S to T, a logical relation over S to T proves statements about V of S, all quantified over all S terms S. So we no longer prove things about just a term, T term T, but we prove things about the outcome of a view application. And here's one example, very roughly explained in one line. Consider the type erasure morphism from Church to Curry. So Church is a theory formalizing an intrinsic type theory where terms carry the type. And Curry is a theory formalizing extrinsic type theories where terms and types coexist and there's a typing judgment between terms and types. And then there's this type erasure morphism or view, which just type erases all types contained in terms. So for an example, consider some Church pair, say just the pair of 1 and 3 of two integers, then this pair would contain the type int. So that this term is an inhabitant of int times int would be encoded in the term intrinsically. After type erasure, we would again have the pair 1, 3, but this time that the actual type int times int isn't anymore part of this term. But still, we would like to type check it against now extrinsically. So what we would like to do is, given a church term, and then applying type erasure, we would like to say that whatever comes out of here is extrinsically typable in the context of query. And this is something logical relations in the spirit of Florian and Christina can encode and can be used for. And now as the last point, as I've already mentioned, Florian and I are not entirely sure how to best represent or make accessible the basic lemma within MMTLF formalizations. So this is still an open question that maybe I could tackle in the course of a master's thesis still. But this is a story for another time. I would like to thank you very much for listening in. And if you're interested, you can drop me an email. Just Google my name, or you can also just go through some references and pointers I have added on the slides here. So thank you.